Hundreds of thousands of raw crude oil flow through a modern industrial processing facility every single day. Managing this massive physical flow requires operating the facility as a continuous, high-frequency decision system. Every hour, operators dictate crude selection, unit severity, stream routing, blending, and market allocation. These choices are tightly coupled. If an operator adjusts a cut point on the distillation column, that single choice dictates the feed quality for the downstream conversion units, which in turn alters the available components for the final product blend. The financial success of these combined choices is measured by the gross refining margin, or GRM. GRM is the total revenue generated from the final refined products minus the cost of the raw crude oil and operations. Because every process relies on the output of the previous one, trying to maximize the efficiency of a single unit in isolation creates downstream bottlenecks. Optimizing locally inevitably erodes the global GRM. Historically, refineries attempt to manage this complexity by dividing the workflow into three isolated tiers: LP planning, scheduling, and execution. LP planning stands for linear programming, a mathematical method used to determine the most profitable operating plan over a long horizon. These tiers operate on entirely different time horizons and rely on different mathematical models. Planning looks months ahead, scheduling organizes the week, and execution happens in the current hour. When an operator at the execution layer alters a unit's temperature to handle a sudden pressure change, that data does not feed back up into the scheduling or planning math. The top layers continue operating on assumptions that are no longer true. When raw crude oil arrives with unexpected sulfur levels, the disconnected architecture prevents the facility from instantly recalibrating its schedules and targets to adapt to the physical reality. This delayed, fragmented decision-making results in what the industry calls hidden value leakage. Millions of dollars evaporate entirely because the facility cannot coordinate its response to real-world disruptions. Installing business intelligence dashboards does not solve this problem. Business intelligence, or BI, refers to software that visualizes historical and current data. Highlighting a structural disconnect on a screen does not physically synchronize the architecture. To eliminate hidden value leakage, the Opti Refinery Suite, or ORS, introduces a unified decision layer. It achieves this using autonomous optimization models, or AOMs. AOMs are independent algorithms designed to solve specific optimization problems while actively coordinating their math with the rest of the network. The architecture of this system begins at the execution level, grounded in physical reality. This base layer contains unit-level models, such as the distillation optimizer and the conversion optimizer. These algorithms operate continuously, recalibrating targets in real time and hourly increments. They adjust temperature cut points and reactor severity by the minute, extracting the maximum economic value out of every barrel currently inside the unit. To prevent the algorithms from making mathematically perfect but physically dangerous recommendations, they are enclosed by the CARE engine. CARE stands for constraint-aware decisioning. The CARE engine strictly enforces equipment limits, ensuring every algorithmic command respects actual hydraulic capacities, safety thresholds, and maintenance schedules. Global optimization is only possible when the base mathematical layer is absolutely bound to the physical constraints of the hardware. Above the execution tier sits the operational flow layer, responsible for facility-wide throughput. Here, the scheduling integrator and tank farm optimizer govern the movement of material between the physical units. Operating on an hourly to daily horizon, these models actively route intermediate streams to buffer tanks, preventing inventory bottlenecks from forming between processing stages.
As the models generate new routing schedules, those instructions feed directly down into the execution layer to coordinate the physical hardware. Next, we add the tactical optimization layer. This grid houses algorithms like the production optimizer and the pricing optimizer. Operating on a daily to weekly cycle, this layer bridges the gap between the physical inventory flowing through the pipes and the near-term economic realities of the market. As external demand shifts and product pricing fluctuates, the tactical algorithms instantly recalculate the optimal blend recipes and product pool targets to capture the highest margins. When those market-driven targets change, the tactical layer instantly overwrites the routing schedules in the layer below it, which then immediately adjusts the unit severities at the base execution layer. By vertically integrating these horizons, the architecture entirely eliminates the reaction lag between an external market shift and a physical hardware adjustment. Finally, the architecture is capped by the strategic economic optimization layer, dictating the long-term commercial posture of the facility. At the center of this grid is the Opti Margin Integrator, or OMI. It works alongside the crude optimizer, selecting the most profitable raw feedstock contracts on a weekly to monthly timeframe. The intelligence of the OMI lies in its absolute authority. It binds all 40 underlying models to a single facility-wide mathematical objective. That objective is maximizing total gross refining margin. By enforcing this top-down objective, the margin integrator forces every lower-level algorithm to abandon its isolated targets and realign with the global financial goal. If achieving maximum distillation throughput creates a costly bottleneck in the blending tanks, the OMI autonomously detects the friction. It overrides the local distillation optimum, intentionally throttling the unit to guarantee system-wide profitability. True system-wide optimization occurs only when a singular economic objective dictates the behavior of every operational model simultaneously. Optimizing for maximum profit is only effective if the underlying physical hardware is actually running. To protect the facility, the core architecture is flanked by the reliability layer. Here, the maintenance predictor analyzes vibration and temperature data to anticipate equipment failures before they cause an unplanned shutdown. On the opposite side sits the simulation layer. The scenario simulator actively runs thousands of what-if models, preparing alternative routing and scheduling plans to handle sudden supply chain shocks. Within this closed loop, physical constraints flow up from the hardware, while economic objectives flow down from the market. The flanking layers ensure that the resulting optimization plan is mathematically perfect, physically executable, and strategically resilient. The downstream industry has operated on ERP systems for decades. Enterprise Resource Planning, or ERP, systems act strictly as systems of record. They log transactions, inventory, and operations only after they have already occurred. In recent years, business intelligence dashboards advanced the industry to systems of insight, visualizing the data to explain why an operational event took place. The Opti Refinery Suite establishes an entirely new layer, the Autonomous Operating System, or AOS. An AOS is a closed-loop platform that continuously decides what should happen next. Instead of relying on manual meetings and massive spreadsheets to coordinate crude routing, unit severities, and blend recipes, the system balances thousands of competing variables autonomously. The human operator no longer needs to chase low-level alarms or manually calculate hydraulic trade-offs under pressure. By removing the burden of manual calculation, the human role elevates from a reactive task executor to a strategic decision governor, steering the entire facility precisely where the market demands.